event that we had, people with cameras on did group activities, and they had like much better communication, and like they were more focused. Or people that looked at black screens, nobody talked anything, and they just stood in silence for 15 minutes and then ended the discussion.
That is quite true, and maybe I could ask that could you each of you at least briefly put the video on so that we can see each other. Unfortunately, we didn't have the chance to start these lectures in classroom, so we would have been seeing each other at least for a while. That would be the best, but now we have to rely on these digital platforms, and if you just briefly put the video on, and if you have trouble with the connection, then you can shut it down, but at least then we can see that we are speaking to another human, not a robot. Let's take the others in also and ask them to do the same. Let's see who we have here. How about Hautran and person whose name is T1953347, Nikita and Danila, could you also put your video for a short while on so we can see who we are?
T195347, it's me just using the computer.
Oh, okay, so you have double identity in the lecture.
Yeah, I do.
Okay, how about Hao and Danila? Can you also put your video on for a while? Maybe they don't hear us. Let's try the chat. Danila is working on it. So you are Mech 18, so it is probable that I've seen some of you in the
We are Mech 19.
Sorry, yeah, you're Mech 19. So yeah, there's a chance that we have seen somewhere in the corridors of the campus, but maybe not that much. Okay, I think it would be if it's okay for you, you could keep the video on. That's much more nice to talk to you when we see each other. I could do that as well, unless the network connection is trying to go sluggish. It happens every now and then, but at least for the time being, I could keep that as it is. Okay. Let's start with the topic for today. Can you see my screen, by the way?
Yes.
Yep.
Excellent. So last time we had a presentation about the screw joints, applications, screws in general. We spoke something about the fastening components, understanding about the pros and cons of a screw joint as a fastening method in comparison to other joint types. We had a discussion about the balance diagram of the pretension screw joint, and we discussed how important the clamp length is on the screw loading and in the reliability of a screw joint that is under tensile load. So just to recap the topic, here is a picture that's been taken from VDI 2230. So that is a German standard for calculating dynamically loaded bolts, well, also static, but the beneficial part of it is from the dynamic loaded bolts. And this basically gives the same idea and information as the presentation last time. So here at first we have the initial state where we have the bolt and the plates. The bolt is the free length is lesser than the plates together, and when we assemble them, we basically force them to be of equal length. And then when we that causes us to have this kind of balance diagram where we have the pre-tension on. So the bolt and the plate, they have the same load in it, and the displacement, meaning the tension or this stretch in the bolt and compression in the plates are different, and that depends on the stiffness of the bolt and the plate. But then when we introduce external load, tensile load to the structure, we find these working states. And in there we have loading, which then can be described working from the load preloading point onto the bolt and also to the plate. And as we learned, if we have a suitably designed bolt joint so that the bolt is of lesser stiffness than the plate, it would mean that the external force is not loading additionally the bolt as much as it's reducing the compression from the joint plate members. So this portion FSA is the addition to the bolt load from the external force. And this FPA is the portion of FA that is sort of consumed by the decompression of the plates. Okay, so this is basically the same thing as described last time. And if you have a chance to upload VDI 2230, unfortunately that is not available in our library in Primo. VDIs are they are not such official standards like ISO or EN standards, but the VDI is I think it stands for Verein Deutscher Ingenieur, so it means that it's an organization of German engineers who have developed this standard, and therefore it's a separately purchased component. I think Beate might have a chance to get this from your university. We don't unfortunately have it publicly available in the library. Okay, so for today we are going to use the VDI 2230 approach in certain calculation. So it's quite extensive, and we are now only using certain part of it. So we are calculating what would be a needed tightening torque if we have to have certain preload in the screw. So what would be the tightening torque that we have to apply to obtain certain preload, and also vice versa, what would be the achieved preload if we have certain given tightening torque. And these calculation examples should give you the understanding of the effect of friction to preload and to the tightening torque. And one hint for you and for everyone is that there will be a calculation according to VDI in the exam, some sort of it. Maybe not exactly in the form as we do it today, but following the same equations and principles, there will be a calculation of VDI 2230 bolt joint. So pay attention to it. And now let's do so that the information is given here in the lecture material. So let's go right away to the task. So the first task is to calculate a VDI 2230 achieved preload force for M12 8.8 joint. And first you need to calculate what kind of preload force you can obtain when your so-called utilization factor nu is 0.9. You will later on see that you will need this character somewhere. And after that, you can calculate what would be the respective tightening torque that you had to apply in order to achieve this preload force. Some information about the joint. The joint members, meaning the plates, also the screw and the nut, they are electrically galvanized, which is quite common. So basically just a zinc coating in the components. And there is a sort of lubricant. In this case, it works as a lubricant. It's a thread-locking glue, Loctite 243 on the thread. So of course, when it's cured, then it's locking it. But while we are tightening, it works as a lubricant. And that is something you need to take into account when calculating the torque. Whereas the nut and the bolt head are dry. So this bolt head against the plates and also the nut against the washer, they are dry. And tightening is done on the nut side. And the whole free-hole diameter is 30 millimeters, which is the standard for M12. And there is no chamfer in the hole, meaning that the whole edge of the hole is sharp. And also you could test when you do this with MathCAD. After calculation, you should check how this preload force changes if you replace the Loctite with oil. And also you oil the bearing surfaces from here and from there. That will have an effect on the result. The utilization factor nu, that's sort of just a ratio or factor which defines how much of the bolt material yield strength we are utilizing with the preloading. And this utilization factor is calculated by this equation in VDI where sigma m Joule, which means sort of allowed stress, zulässig Spannung in German. So that describes the allowed preload tension due to the preload and also due to the torque from the tightening. And ratio of that to the proof strength, meaning the yield strength basically of the material, is the utilization factor. And usually the utilization factor is given as 0.9. That is quite normal. So we utilize 90% of the yield strength of the material when we apply the tightening torque. So this is just a factor that you need to use. And also it was given here that nu is now 0.9. And the maximum allowed preload stress you can calculate with this equation. There is the utilization factor and there is the yield strength. And the yield strength for this bolt material, you already know how to calculate it. We learned it last time. So you know what is the method of obtaining 8.8 grade yield strength. It's basically given in this designation. And then the rest of the values you need, diameters, P is a pitch, and frictions, you will need to find from the following tables. There are thread dimensions, friction coefficient for different kind of pairs of materials with different lubricants applied. And one addition to the diameters. Now these tables are primarily taken from ISO dimensions. And there's, in a couple of places, there is a deviation to the designations compared to VDI. and that is being stated where is so. So in these tables for ISO NUT dimensions, we have this lowercase d subscript a. That stands for the internal diameter of this NUT hole. Also, sorry, not the hole, but the internal diameter of the NUT bearing surface. So basically, just outside the thread, the bearing diameter, bearing area diameter in the NUT, and that is in the VDI used written in capital D subscript A. But that is the same. So in the equation, there's a capital D A, but in the table you will check this lowercase d subscript A, just to take it into account.
Excuse me, can you
Yes.
repeat again? What is the difference between DA and D capital D?
There is, I don't know what is the reason for it, but just that the standard VDI is using different designation for this dimension. So in the ISO, there is a smaller case d. In the VDI, there's a capital D. And what is the reason? I don't know.
And also there's a D above the DW capital on the
There's DW. Yes.
On the drawing of the not there's a capital D. Yes.
Yeah.
And how it is differ from DA?
That's a good question. That's that means the nominal diameter. So the capital only capital D means the thread size. So the nominal diameter of the bolt. So the outside, basically the outside diameter of the screw here, thread D.
So it should be M something.
Yes, exactly. So for M10, the D is 10 millimeters. Capital D is 10 millimeters.
Yes, thank you.
Okay, so go ahead, start the calculation, and please ask right away if you encounter any troubles. But basically, you should be able to find all the needed parameters for this equation, and also for this equation from the tables. Okay. So the first step for you would be to calculate the allowed stress, so this sigma m Zul, applying the given utilization factor, which was 0.9, and with the yield strength or proved strength of the material of the bolt, which you can calculate as you know that the strength grade is 8.8. And then you'll find from the tables the diameters D2, D0, pitch P, D2, and the minimum friction coefficient in this thread.
So at the exam, we can use all our calculations that we do in MathCAD now. Am I correct?
Sorry, could you repeat?
Yeah, so as far as I remember, you told us that at the exam we will be allowed to use all our calculations with MathCAD that we did. Am I right?
Yes, you can utilize all the calculations that you did while these lectures using MathCAD. So, but just that in the exam, if the exam and when it's going to be fully online, fully remotely done, you have to also make the hand calculation and then send the picture of that to me. So, but you can of course utilize these calculation sheets that you've done using MathCAD.
I see.
Yeah, and you can also use the MathCAD as a calculator in the exam. Just that you need to do the hand calculation as well.
Great, thank you. It's all clear now.
So the value I got from the calculation was 447.9 megapascals for Sigma M Zulu.
Can you repeat?
It's also in the chat, so it's 447.9 megapascals. What I got as a result, and then the resulting preload would be this FM Zul, and I got it 34.1 kilonewtons. So the force is of course just plainly stress multiplied by the area.
Yeah, I probably missed it, but where do we take mu value? The one like mu g meant in the round brackets.
That is the friction value, and that is friction in the thread, and that you need to check from the let's see the page for the frictions. It is slide number 14.
Let me check it.
Sorry, it's for the bolt head. So for the thread, it's slide number 9. Yes, mu g is the friction coefficient in the thread. It's on the slide number 9.
Oh, I see it. Yeah, I see it now.
Yeah.
Thank you. So do we assume that it's dry for the one case and then oils for the other case?
You should check the assignment. So in the task assignment, it said that these nut and bolt head are dry, but in the thread where the mu g is affecting, we have this Loctite glue that is affecting the friction mu g.
I'm a little bit confused then, because we have friction coefficient in thread, and we also know that the thread is glued. Let me check this. Yeah, so this thread is glued with Loctite. Therefore, which value should we choose with this?
Check the slide number 9 and read all the text through. It's not given in the table, but below.
Is glue considered like anti-friction coating, or?
No, but it's the thread locking agent.
Yeah, makes a lot of sense though. So, and then we just pick a random value between 0.2 and 0.3, or should we also?
Then it's up to you to consider which value you would use. But if you consider the situation that you want to calculate you want to find that the maximum preload force in this case. So would you use the maximum or minimum friction then?
Yeah, I'd use, because we then divide all this, I'd use the minimum friction.
Yes, exactly. Because when you have less friction, it will mean that you will, with the same torque, you can tighten the screw more tight, and you will obtain more preload force. So that is why you should use the minimum friction when you want to obtain the maximum preload. And also, if you want to obtain the sort of minimum preload or calculate what is the minimum preload, then you would need to use the maximum frictions.
Yep. Thank you. This is makes a lot of sense and helpful.
I'm not sure if my written values, can you see them in the chat, by the way?
No,
No,
I
we
cannot
cannot.
see anything.
Uh-huh. Let's put it again, because it's for some reason it went to everyone in the waiting room. I don't know why. Okay.
No, we can see them.
Yes, now we can see it.
Slide 7. Let me check. Yeah, there's just a missing multiplier sign. Jaakko, you're right about that. Yeah, true. Yeah, yes. The straight bracket, it doesn't mean a vector or matrix. No, in this case. It really makes this following the equations a little bit difficult when the VDI uses slightly different designations for certain characteristics comparing to ISO. So that's a little bit maybe tricky. I don't really know what is the reason or the history behind, but we just need to live with it. And the key thing when you apply this equation, as you note, the friction in this thread affects to the allowed stress. So the more you have the friction, the more of the torque is going to be consumed by the friction. And therefore, the higher the coefficient of friction, basically you can obtain more less, you will obtain less preload in the screw.
I got like 59 kilonewtons, so I think I messed something up.
59. Yeah. Did you get the same stress value anyway?
Yes, I got 447 megapascals. So
And
I think I
now
messed with the area.
yes, you probably messed with the area. So the area you should be using is the core cross-section, the A0 according to VDI, but it's A3 according to ISO 965.
Okay, let me try to find my mistake. Yes, I just had a wrong cross section. So now I got it right.
Okay, yeah.
Excuse me, I cannot see why is why is the bolt size we are using. I just see the whole diameter is 13 millimeters. Did I forgot something?
Sorry, could you repeat what was the problem?
Like I didn't see why is the bolt size, and I just can see the whole diameter is 13 millimeters.
Yes, but the bolt size is given in the task assignment. It's M12.
Oh yes, sorry.
So Pirkkonen got it right. 93 Newton meters if you apply minimum DKI diameter. But if you apply maximum DKI, then there's a slight difference. There's a 94 Newton meters. And the reason is that when the DKI, it stands for the friction area under the nut which resists the tightening torque. And of course, if you have a bigger friction area diameter under the nut, it means that there's more to resist the torque. And eventually you will need more torque to obtain the same preload force as it would be for a smaller friction diameter. But not that big difference anyway. But now if you do the recalculation, you've done it now. So if you update now your friction values for the ones that you would have when the thread is oiled and when the nut bearing surface is also oiled, you will see a drastic difference in the required torque and also in the preload force. So now you see in this you can see the benefit of MathCAD. If you would need to do this with hand calculation, you would write again everything again and put it again in the calculator. Now you just need to update two figures and you got the result. By the way, we could now do so that if you have some individual questions of the project work, we could do so that I will take the separate breakout room sessions in here now. If somebody of you needs assistance in the project work, are there anyone needing guidance to that?
I had some when choosing the radius of the chamfer.
Okay. Is it okay to you if we'll take the breakout room session right away?
Maybe yes.
Okay, just a second.
Yeah, so Tom, are we free to go then, if we don't have any questions for now regarding the project work?
Yeah, of course you are free. Generally, otherwise also no lesson is mandatory. So if you are adult people, so if you think that you can learn these just by reading the lecture materials, it's fine also. If you feel that you have enough information and you can perform the calculations also by your own, you are free to go, of course.
Okay, maybe I should structure my question a little differently. So, is there any other material going to be presented at this lecture today?
No more material. So this lecture for today is in the Moodle, and that's all for today. Probably we are not having enough time to do the calculation for task number 2, so that remains to be done next time. So, but do as far as you can. So.
Okay, I'll do then. Thank you.